This program is brought to you by Stanford University. Please visit us at stanford.edu.
Classical mechanics is the basis for all of physics. It's the basis of all of physics, not only because it describes the motion of objects like particles and mechanical systems and so forth, but because the basic framework, the basic structure of all of physics is based on the principles of classical mechanics. The conservation of energy, the conservation of momentum, the principles by which all systems evolve in nature is the same set of rules, essentially exactly the same set of rules in a more abstract and a more general setting than the rules which govern how a simple particle moves, for example, under the influence of gravity. But in order to understand it, we have to understand the principles in a fairly general context. Let's begin with the very, very simplest kinds of systems that we can think of. Systems that are so simple that, in fact, they're simpler than any real systems in nature. Laws of nature, let's imagine laws of nature which are of the most primitive and simple kind, acting on the most primitive and simple systems that we can imagine. I want you to, first of all, suppose that time, which evolves continuously under my watch, I see the second hand goes around and around and around, it goes around continuously. The time can evolve and be any real number, t. I want you to imagine it only occurs in beats. A stroboscopic world in which you only look at the world at intervals of time, which could be 1,000th of a second, or it could be 1,000,000th of a second. Let's just take it to be 1 second intervals and ask how, in the stroboscopic world, systems change with time. Let's also imagine a very, very simple set of systems. Systems which are so simple that they only have a handful of configurations. Configurations mean everything we need to know about the system to characterize it completely. So the simplest system I can think of would be a system that has only 2 configurations, heads or tails, a coin. Lay a coin down on the table. I don't have a coin, so we'll take this coffee top here. I could put it down heads, or I could put it down tails. I doubt if you can tell the difference from where you're sitting, but I can tell the difference. This is heads, that's tails. All right. So we have a system then that's characterized by 2 states. 2 states of being. And we want to add to those 2 states a law of evolution in going from one instant of time to the next instant of time, from one beat of the stroboscopic light to the next one. What kind of laws are allowable? What kind of laws do the basic principles of physics allow, and what kind of laws don't they allow? That's going to be our first kind of question for tonight. So our first concept is the space of states. In this case, just heads and tails. It's just 2 points, heads and tails. So 2 points in an abstract space, heads and tails. It's called the phase space. It's called the phase space of a system, the space of possible states of a system. And what do I mean by a state of a system? I mean everything that you need to know in order to predict what happens next. Everything you need to know in order to be able to say with certainty what the next state of the system will be. That's called the phase space of the system. In this case, just heads and tails. What kind of laws can you imagine? What kind of laws of nature can you imagine for this extremely simple world? It is the simplest. Well, I suppose you could imagine a slightly simpler world. You can imagine a world with only 1 state. Heads. Not much can happen in that world. There's only 1 law of physics. Heads goes to heads, and heads goes to heads goes to heads. It's extremely boring. Nothing ever happens because there's only 1 state. So how could anything happen? But with 2 states, heads and tails, you can have a richer variety of possible laws of physics. One law, let's take the various varieties of laws of physics we could have. One law might just say, you stay the same. If the state of the system is heads at one instant of time, then the next instant of time it will be heads. If it starts tails, it will stay tails. That's a very boring law, and let's graph that law by drawing an arrow. If it starts heads, then it stays heads. Let's just represent that by drawing an arrow from head to head and from tail to tail. The meaning of this arrow, you start at the tail end of the arrow, and you follow it, and you see that it comes around to the same point. That stands for the rule that says that a heads stays a heads, and in this case, a tail stays a tail. So there's a very dull law of nature. This stays that way for endless amounts of time, and this stays that way for endless amounts of time. Another possible law of nature would be a slightly more interesting situation. If you look at it at one instant of time, the next instant it's the opposite. Heads goes to tails, goes to heads, goes to tails. These are deterministic laws. Deterministic laws mean that if you know what is happening at one instant, you know forever after. You know everything about the system infinitely into the future. Completely deterministic. Classical mechanics has that nature to it, that it is completely deterministic. And in fact, it is in a certain sense always reversible, but we're coming to that. All right, so to draw the graph representing heads goes to tails and tails goes to heads, we draw an arrow from heads to tails and from tails to heads. And we read that as saying that if you start at heads, you go to tails. If you start at tails, you go to heads. What is the evolution of a system under this law of nature? If you start with heads, it's heads, tails, heads, tails, heads, tails, heads, tails, forever after. These are two consistent laws of physics in a world of only two states. Okay. Whether we can think of more laws, yes, we can, but for the moment, these are two interesting ones. Now, how can we generalize this? We can generalize this, first of all, to systems with more states. Two states is not very many. We could have a die as in dice. A die has 6 states. 1, 2, 3, 4, 5, and 6, and we could represent them as points, 6 points. Now we have a large variety of different laws of physics that we could have. For example, we could label these 1, 2, 3, 4, 5, and 6. Which one is 1 and which one is 6 is not very important, but there are 6 of them. We could have a law of physics which says 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes back to 1. This would be a complicated motion when thought of in terms of a die. You start with a 1 up, and then it goes to the 2 up, 3 up, and so forth. But it's a relatively simple picture when drawn in this manner here. You can imagine more complicated laws of physics with 6 states. Well, whether they're more complicated or not is in the eye of the beholder. But first of all, we could have a similar law where instead of 1 going to 2, 1 could go to 3, 3 could go to 2, 2 could go to 5, 1, 2, 3, something like that. That's really not very different than this. Each one goes to a neighboring one, well, not to a neighboring one, each one goes to a next one, and they cycle around. And one characteristic of such systems is they will just cycle around forever and ever and ever. Okay? Now, you can have more complicated, I don't know if they're more complicated, different laws. For example, you could have a law which goes this way. If you start at 1, you go to 2. If you go to 2, then you go to 3, and then you go back to 1. If you happen to start at 3, no, this isn't 3, this is 5, right? 5. 6. 1, 2, 3, 4, 5. If you start at 3, you go to 4. If you start at 4, you go to 5, back to 3. In this case, well, that's somewhat similar to this. You have 2 disconnected cycles. We can have more complicated things. Here's another one. In fact, I think it would take a long time to draw all the possibilities. 1 goes back to 1, 2 goes to 3, 3 goes to 4, 4 goes back to 2, 5 goes to 6, and 6 goes back to 5. Right? They're all acceptable laws of physics. Wherever you happen to be, you know exactly where to go next. So it's deterministic. It's deterministic into the future, meaning to say wherever you start, you know where you will be arbitrarily into the future. If you start here and you go 100,000 times, you'll just wind up, I don't know, somewhere, wherever. If you start here, you stay there. So these are completely deterministic into the future, but they're also completely deterministic into the past, which means if you know where you are, you know where you were before. If you find yourself over here, then you know in the previous cycle or the previous instant you were over here, and so forth. So you can trace your motion either into the future or into the past with complete confidence about where you'll be no matter how far you go. That's the character in principle, if not in practice. In practice, things get jumbled up and you can't see them clearly enough and you miss detail. But if you could see the infinitely small detail in a system and get every single bit of physics absolutely right for any classical system, they are, in this sense, exactly deterministic, both into the past and into the future. Now, what kind of laws of physics do we not allow? The kind of laws of physics that we don't allow, I can best illustrate, I think, by drawing some possibilities and explaining to you why they are not allowed. Here's a law of physics that is not allowed by the principles of classical physics. 3 states. 3 states is perfectly all right, nothing wrong with that. But let's draw some arrows. 2, 3, 2 goes to 3, and 3 goes back to 2. That would be perfectly all right by itself. What about 1? Well, I could have 1 goes to 1, but I don't want 1 to go to 1. I want 1 to go to 2. That's completely deterministic into the future. If I start at 1, I go to 2, I go to 2, I go to 3, I go 3 back to 2, 2 back to 3. I always know where to go in the next step. I just follow the arrow wherever it happens to be. But what does it fail? It fails to be deterministic into the past. Supposing I know that I'm at 2, then where did I come from? I could have come from 1, or I could have come from 3. So I cannot work my way backward with uniqueness. I can work my way forward, I cannot work my way backward. This is a law of physics which is irreversible. It would not allow me to run the laws of physics backward. It would lead to an ambiguity every time I were at 2. Another law which is not allowed by the principles of classical mechanics or principles of classical physics would be basically the same thing, but with the arrows turned in the opposite direction. All arrows reversed. Here I have a problem not going into the past, but I have a problem going into the future. Let's see. Supposing now I find myself at 2 and I want to go into the future. I don't know whether to go into the future by following this arrow to 1 or this arrow to 3. There are 2 arrows leading out of 2 over here. One of them goes to 3, one of them goes to 1. Nothing tells me which arrow to follow, so it's not deterministic into the future. I might randomly decide to go from 2 to 3, or randomly decide to go from 2 to 1. These are rules, each one of which is deterministic in one direction, but not the other. These are the sorts of things which are forbidden by the principles of classical mechanics. Why are they forbidden by the principles of... Yeah.
What if you just erase one of those lines, one of those with...
Which one?
Yeah, just one of those 2 lines on the loop there.
Here? That wouldn't tell me, I wouldn't know where to go from 3. You get stuck at 3.
Yeah.
Yeah, no good.
Can you ever have, say, a dangling 1 over here?
No, you can't have a dangling one. You got to know where to go next. Now, you could, let's see, we could try to put something like that in.
Yeah.
Okay, so that would say we go from 1 to 2, from 2 to 3, to 3, to 3, to 3. Now, the problem would be in going backward, I think.
Right.
Yeah.
You don't know where you come from,
Yeah.
3 or 2.
Yeah, right. So one way or the other, you get stuck with these rules. All right, how do we spot what's allowable and what's not allowable? Well, it's very simple. At every configuration, 2, 3, we should have 1 in and 1 out. We should have a unique 1 in, a unique arrow in, and a unique arrow out. 1 arrow in to tell us where we came from, and 1 arrow out to tell us where we're going. That's the character of classical physics. Uniqueness into the future, uniqueness into the past, when represented in terms of this very simple and analog world, digital world of a finite number of states, then the rules of physics, as we know them, would say every configuration has 1 in arrow and 1 out arrow. Now, with this rule, of course, life is very boring, because if you only have a finite number of states, all that can happen to you is you cycle around endlessly among those number of states, always in the same order. You can have slightly more interesting situations. There's no reason why the number of states has to be finite. You could have a situation where there's an infinite number of possible states. A state corresponding to every integer, positive and negative. A particle on a position on a line where the position could be any integer value. And then a simple law of physics would be you go from one to the next. Wherever you are, you go to the next one. Each point has 1 in and 1 out. I can't draw them endlessly. It'll take forever. But each mark, 1 in and 1 out. This, of course, would also be a rather boring law of nature. You just hop from one to the next, to the next, to the next, to the next, forever and ever and ever. But at least you wouldn't be cycling around endlessly. Again, we could add some more states onto this. We could add this on. If we start on the line, we simply move off and keep going forever and ever and ever. But if we start over here, we cycle around. So we could have mixtures of both kinds of things. Some states we cycle around in, other states we move off to infinity. Now, notice that some of these laws of nature, the phase space breaks up into different pieces which are connected among themselves but not connected to each other. For example, even with just 2 states, we had 2 possibilities, one like this and one like this. In this case, where it breaks up into more than one piece, we have something called a conservation law. A conservation law is simply a memory of where we started. A conservation law means that something is kept intact for all time. Some piece of knowledge is kept intact for all time and doesn't change. In this case, we could label a configuration over here with a +1 and a configuration over here with a -1, and then we could invent a variable, +1 over here and -1 over here. It never changes. If it's +1, it stays +1. If it's -1, it stays -1. That's a conservation law, something which doesn't change with time. On the other hand, if we hop from +1 to -1 to +1 to -1, we don't have a conservation law. Conservation laws are always associated with these kind of closed families of different trajectories in the phase space which don't mix with each other, which remember something about the system which might otherwise get mixed up if everything got all mixed together. So there's all kinds of possibilities that are inherent in these deterministic laws, but always the condition is one inline and one outline for every point. That can also be called information conservation. It's information conservation in exactly the sense that you never lose memory of where you started, either into the past or into the future. If you know where you are at any instant, you know where you came from and you know where you'll be. Information about where you are is conserved, never changes into the past and the future. Whereas if you have one of these bad laws, laws which are forbidden by the rules of classical mechanics, then you do lose information. For example, if you find yourself over here, you don't know whether you came from here or from here. Well, no, that's not quite right. If you find yourself over here, you don't know whether you came from here or over here, so you lose information. Information conservation is perhaps the most fundamental law of basic classical physics, that you don't lose information about. Now, why is that so? It's not written into the laws of physics why they are what they are. Maybe someday we'll understand hyper laws of physics or meta laws of physics or deeper laws of physics, which will tell us why the laws of physics are what they are. At the moment, it's more or less an experimental fact that all the known laws of physics fit into this class of information conserving laws, even those which are quantum mechanical. But for our subject this quarter, we're only interested in classical physics. All right, so that's the basic setup if we were interested only in this stroboscopic world of discrete time intervals. The real world, of course, is more continuous than that. Supposing, okay, so let's make the law something like this. If the last two states were heads-heads, then it stays heads. If the last two states were heads-tails, then it goes to heads. If the last two were heads, tails, heads, then it goes to tails. And if the last two were tails, tails, then it goes to tails. I think that's a possible law. Then you would say, I can't tell from the fact that it's heads where it goes next. And indeed, I can't. But that would just be another way of saying that a specification of a heads by itself is not what you would call a state. What you would call a state would be the specification of the previous last two entries, because you need two entries to tell you what happens next. Now, that raises the question that's very, very important in classical mechanics. How much and what exactly do you need to know to say what happens next? If the phase space is the space of things, space of possibilities, but always in such a way that they tell you exactly what happens next, what is it that you do have to know next? So that brings us to continuous physics. Let's take the motion of a particle. Let's take the motion of a particle. Is it enough to know where a particle is to say what happens next? Let's hypothesize that the generalization to continuous time is that we need to know the exact location of a particle along a line. We've run out of ink, I'm afraid. There it is. All right, so let's imagine the motion of a particle along a line. All right. Then you might think that the analog of a state is just the location of a particle. Where is it? But is it enough to know where a particle is in order to say what happens next? No. What else do you need to know? Its velocity. In order to know where a particle will be next, you need to know not only where it is, but how fast it's moving. You need to know its velocity. So that means the state, in the same sense that I used it, that which you need to know in order to know what happens next, does not just consist of the location of a particle, but you can say it two ways. You need to know not just the location of the particle, but you need to know also the previous location, or better yet, what is equivalent to knowing the previous location, the velocity. right, the velocity. That tells you that the phase space, the space of states, the space of configurations, is two-dimensional, not one-dimensional. It's not just a line. It's a line that represents the position of the particle, and a second line which represents its velocity, either to the left or to the right. Positive velocity means moving to the right. Negative velocity means moving to the left. Supposing you're over here, where do you move next? You stay the same place. Why? You're at the origin and you have no velocity. What if you're over here? So we could draw a little loop here to say that you come back to the same place. What if you're over here? You stay the same place because you're moving with zero velocity. Vertical axis is velocity, so you come back to the same place. What if you're over here? Where are you 1 second later? Let's chop time up into 1 second intervals. Where are you next? Somewhere to the right, huh? What if you're over here? No, what if you're over here? Move twice as far, or roughly twice as far to the right. What if you're down here? You move to the left. So we could fill up this space here with little tiny arrows to show where you move next. But notice, to know where you move next, you have to know not only where you are in the sense of what x is, but you also have to know the vertical component, namely what the velocity is. So that means the analog of a point in the phase space is a point in the space not only of positions, but also velocities. Yeah.
So there's a conceptual issue here that I don't understand. That is, you would think that if you were able to discretize time finely enough,
Yes.
the two should be the same. And yet,
Why?
you have a velocity that came in, which isn't readily apparent where that would take place if we had these infinitely small, discrete time
It means,
representation of that.
no, it means exactly what the gentleman asked me before. What if you had a law of nature which tells you in order to know where to move next, you had to know your previous two entries? All right? Now, one way of saying it is, all right, in that case, I need to know the previous two entries, and it just doesn't fall into this class of things. Or you could say that the space of configurations doesn't just consist of a heads or a tails, but it consists of a pair of entries, a pair.
So we can model that with
Yeah.
discrete time the same way.
That's right. We model that.
Just need the last two.
That's right. We need two axes instead. That's right. We need an axis for the present configuration and the past one. Yeah. That's exactly right.
Also, in classical physics, do you ever really know your state?
Well, of course not, because in classical physics, the position of a particle and so forth is a real number. A real number is something that you can never determine exactly. And so there's always imprecision, and that imprecision always represents a degree of uncertainty in where you will be next. Now, it gets worse and worse in general. It's likely to get worse and worse as you try to take larger and larger time intervals. A given degree of imprecision in what you actually know can get magnified and get magnified into worse and worse imprecision as time goes on. So in practice, classical systems don't really have the property that you can predict endlessly where they're going to be and exactly what they're going to do. But you can always say, given a time interval, I want to be able to predict exactly for the next 30 seconds where every molecule in this room will be. Let's forget quantum mechanics now. I want to be able to predict exactly where every molecule will be. Then there's a certain degree of precision in the present information at exactly one instant of time, which will permit me to be able to extrapolate for 30 seconds. Okay? It will not permit me to extrapolate for 40 seconds. If I try to extrapolate for 40 seconds, I will find the errors get magnified out of control. If I want to predict correctly for 40 seconds, I will have to do even better in my initial conditions, in my knowledge of exactly what the state of the system is. So in practice, this idea of determinism is defective. It's defective because in order to determine for a given length of time, you have to have precision, which is so good that it's way, way beyond anything anybody can do. But in principle, given any length of time in classical physics, there exists a degree of precision which allows you to extrapolate for that length of time. Does that answer the question? Yeah. Some systems are very predictable. Some systems are less predictable and get out of control very quickly. They're called chaotic systems. But the principles are the same, that it's just a degree of precision which you need to know in the beginning in order to extrapolate for a given length of time.
You could say the system is still deterministic, it's just not predictable.
Well, you could. I'm not sure what the difference between predictable and determinable. The way I use the terms, I use them interchangeably, so I can't say that.
I think they're conceptually quite different. And you could say that these are the equations that match reality, and they are deterministic. There's no way out, except that they don't give you an algorithm to predict, because prediction requires measurement.
Okay. Okay. Yeah? Right. What's that?
There is a probability of predictability.
Yeah. Right. The equations are deterministic if you know the initial conditions are deterministic, are predictable, infinitely predictable if you know the initial conditions with infinite precision. You never do, and therefore they're never completely predictable. Now, the fact that you need to know both the position and the velocity in classical physics in order to predict what happens next reflects itself in the structure of the equations of mechanics. Specifically, it tells you that the equations of motion, Newton's equations in this case, are what are called second-order equations instead of first-order equations. Let me illustrate it by starting with a first-order equation. A first-order equation, what a first-order equation means is that it only has quantities of first derivatives with respect to time. In other words, only contains velocities. Second order means it contains not only first derivatives, but second derivatives means it contains accelerations, the equations of motion. Acceleration is the second derivative of the motion. We could write, we know what the real equations of motion of Newton are, F equals ma. It contains acceleration. Let's write a phony equation. Let's write F equals mass times velocity. Force is F, velocity is velocity. And let's suppose that force just depends on where you are. We have a particle that moves along a line. It's subject to forces which vary along the line. Right? Force may be big here, small there, and so forth. So the force depends on position. And let's imagine this fake equation of motion that it's equal to mass times velocity. And what is velocity? Velocity is the time derivative of the position, the x by dt. And I will use continuously throughout this course the notation that time derivative is just indicated by a dot. Dot means time derivative. All right, what does this tell me? What do I need to know in order to predict what happens next? I say for this equation, we only need to know the position of a particle. If we know the position of a particle, I can tell you what the velocity is, just from the equation. If I know that the position is a particular position, then I know the force on it, and from the equation, that tells me what the velocity is. Does it tell me the acceleration? How about the acceleration? Let's see if I can compute the acceleration. To compute the acceleration from this equation, we just differentiate it once more. We write that df by dt is equal to mass. Mass is just a constant times the second derivative of the position, or just the acceleration. So we have over here acceleration. What about the f dt, the time derivative of the force? The force varies with time because the position varies with time. Right? So df by dt is just a reflection of the fact that the position of the particle varies with time, and we can write the f by dt using the standard rules of calculus as just the change in f with respect to position times the change in position with respect to time. In other words, the velocity. All right, we've already figured out what the velocity is, knowing the force, knowing the position. So we know the velocity, and we can read off from this equation what the acceleration is. We can figure out all of the derivatives of the motion if we know where the particle is by multiply differentiating this equation. So what it tells us, to make a short story out of it, is it tells us that if we know where the position of the particle at any instant of time, then we know where it's going to be in the next instant, the next 2 instants, the next 3 instants. It completely predicts the motion. But this is not the character of Newton's equations. Newton's equations say F is equal to mass times acceleration, not mass times velocity. So let's look at this equation. F equals mass times acceleration. Can I predict from this what the velocity is? No. There's just no equation for the velocity. Right? If I know what the position is, I know what the force is. That tells me what the acceleration is, but there's nothing in these equations which tell me what the velocity is. That means I have to add in the velocity as a piece of information to begin with. I have no choice. I have to tell you, in order to predict, I have to tell you the position as well as the velocity. Then, if I know the position and the velocity, I can then predict the acceleration, the next or a third derivative, the fourth derivative, and all of them. So that tells me that in order to know where I am and where I'm going to be, I have to know the position and the velocity. The phase space is a two-dimensional space. So we see then that that classical mechanics does have this character of a configuration or a phase space of different configurations with a set of little arrows which tell you where to go next, but the phase space itself has a position component to it and a velocity component to it. All right. We will go on and study the classical equations of motion and study them in a variety of different formulations, but always the connecting link will always be conservation of information, the idea that the laws of physics are completely deterministic and described by equations which tell you where you will be next. That's the character of classical physics. Okay.
As a result of this bifurcated system,
Bifurcated.
the heads and tails up, instead of being one system, you need two pieces of information, not just one.
It's one system, but you need two pieces of information instead of one, yeah.
If it weren't bifurcated, then you would.
I'm not sure what you mean by bifurcated.
Two pieces, like heads and tails up there, the very top.
Up here, here you only need, no, here you need one piece of information to say where you'll be next. If you're here, you stay here. If you're there, you stay there.
But the system is heads and tails.
The rules
Yeah.
are complicated, but the states are only one piece of information.
It's just, all there is heads and tails. That's all there is. And if you know where you are, you know where you'll be next.
You know, when there were 6 states, then he had 6 rules. You can have more rules, but basically
No. No. There's one rule.
coordinate for the what the dice was initially. So you only had one piece of information that you needed.
No, this is one rule. Heads goes to heads, tails goes to tails. That's a single rule. And if you know that you're at heads, then you know you'll be next at heads. If you know you're at tails, you know so you only need a piece of information, heads or tails. That does it. That tells you everything. Now, I suggested a different, You don't need to know where you were before. You only need to know where you are now to know where you'll be next. So both of these laws require only knowledge of where you are at one instant to tell you where you'll be next. You simply follow if you start someplace, you follow the arrow until you come back, or you follow the arrow till you get to the next place, and that tells you where you'll be next. You don't need any more information than that. The only question is what one of these points corresponds to. Does one of these points correspond to, how much information does it correspond to a point in the space? Is it enough to know heads or tails to know what you'll do next? Or might you need to know the two previous things? That's a different setup.
Okay, if you have a single particle in free space, then that has 6 phase space coordinates.
Let's stay with the heads and tails for a minute. Let's suppose that in order to say what happens next, you need to know the previous two configurations. Let's work out that example, and let's write it in this form. All right, let's make up a law. I think I had one down before. Heads, heads goes to heads. Heads, tails goes to what? Tails? Tails, heads goes to heads, and tails, tails goes to tails. Okay? Is there something wrong with that?
It only requires, we gotta switch one of them. It only depends on the last state. Heads go to
Oh, this only depends on heads go to, you're right. Sorry. Heads, yeah. We want this one to go to tails. Second one goes to heads. Good. Yeah.
That won't work. The first, then two will work. The first one.
What? Say it again?
Then what happened 2 times ago matters, but not the last time.
That's also true. Yeah. See, it looks a little hard to work an example, doesn't it? Let's see.
Switch the second one and that'll do it. Switch the second one.
Switch the second one. This one?
Yeah, make it tails.
Make it tails, okay. I think that's perfectly all right. You lose information? Why? Well, okay, here's a setup. If you know the previous two, then you know what happens next. In fact, let's now see if we can make a table out of this. Not a table, but a set of points. A set of points, then there are 4 possibilities. Heads, 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 tails, tails, heads, and tails, tails. Okay, let's see. Here's heads, 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 tails, tails, heads, and tails, tails. Now, supposing you go from heads, heads to heads. So this is heads, heads, heads. That means you go from heads, heads to heads, heads. Right? You go from heads, heads to heads, heads. Now, supposing you go from, let's see what happens. If you start with heads, tails, where do you go to? So you go from heads, tails to tails, tails. Okay? Okay, what happens if you go from tails, tails? Oh, we're going to run into trouble, aren't we? Tails, tails goes to tails? So tails, tails goes to tails, tails. Bad. Not allowable by the laws of physics. And now tails, heads goes where? Tails, tails goes to tails, tails? Wait. Tails, heads. Tails, heads goes to heads, tails. So that goes here. Well, it seems to me we should be able to make a consistent law. What the? This one? This one. Oh, tails goes to tails goes to heads. Yeah, okay. So then tails goes to heads, and that means that tails heads. So that means tails goes to tails heads. Ah. Oh, okay, good. Now we have a workable law. The only thing we had to do was to say that what we originally called a configuration, namely a single heads or tails, was not a complete specification of information. A complete specification of information involved two pieces of information, and once we recognized that, we were able to write this down as a law of physics, which is deterministic and reversible. Okay? So you don't know offhand, you don't know to begin with what pieces of information you need to know in order to know what to do next. But that's what the configuration space, or that's what the phase space is. It's the collection of all the things you need to know what happens next. Now, of course, you could go beyond this. You could say, I need to know the first three things in order to know what happens next. You can do that. You'll simply need more states to make a deterministic system. What would it mean in classical mechanics to need more information than the positions and velocities? Suppose you needed the positions, velocities, and accelerations. That would mean third-order differential equations, but what would it say about the phase space? It would mean you would need positions, velocities, and accelerations to represent the phase space. Okay. As it happens, that is not the case for classical mechanics. That's an experimental fact. But it wouldn't stop us if we did need the accelerations. We would just write third-order equations, and we would make our phase space three-dimensional.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.